This is lecture 2.5, and I will talk about cyclic groups. So a definition is very simple and very general. So definition: a group G is called cyclic if there exists an element G inside G such that every element of G is a power of this little g. So every element of G is a power of this little g. That's condition when G is cyclic. So here are some examples. So maybe the simplest example is one can take integers. And integers form a group if as operation I use plus. So the inverse is just minus the corresponding number, and identity is 0, of course. So that's a group. And then indeed, so if I take any integer n, this will equal to kind of 1 power n sort of, because operation power n means here 1 plus 1 plus 1 n times. So power means also negative power, and negative power in any group is defined as to take the inverse and takes n power, which means inverse times n times. And so, of course, minus n will be 1 power minus n, sort of, which means minus 1 minus 1 minus 1 n times. And 0 is 1 power 0. So, of course, this is kind of misleading notation. So this is an example of a group which has this property. It's called cyclic. And another example is, of course, one can take S2. And the reason is because it has just 2 elements. So it has 2 elements which are identity and permutation 1, 2. And so every element is a power of 1, 2. This is 1, 2 power 0. And that's 1, 2 power 1. So here is another example. So consider a regular triangle T, and let's consider a group of rotations fixing this triangle. So that's actually a group of orientation preserving isometries of the triangle T, which consists of 3 elements, as we already discussed: identity map, and then its rotation with a center O by 2 pi over 3 angle, and rotation with a center O by 4 pi over 3 angle. And this is a square of this one. So that's rotation O 2 pi over 3 squared. And so if I denote it by G, that's identity, this is G squared. And so all elements are powers of the same element G. Okay, so these are some examples. And here is an interesting theorem. So proposition: every group of prime order is cyclic. And the proof just directly follows from Lagrange Theorem, basically. So Lagrange Theorem. So Lagrange Theorem from homework. So let's consider any group G, and suppose that G has P elements where P is prime, and this is the number of elements. So take any G in G, where this little g is not identity. Just any other element except identity. If G has just one element, that's not hard to see. So then we know that we can look at the order of G, and I remind you that this is the minimal number k, minimal k, such that G power k is identity. And when we discussed during office hours the proof of Lagrange theorem, we saw that order of G divides the order of the group. And the reason was because we looked at all elements in the group and looked at multiplication by G, and we saw that there is a bunch of cycles here. So, and the group is a union of cycles of the same length, which is this one. And so G is the order of G is equal to the number of cycles times the order of G. But this means that since this is a prime number, order of G is either 1 or P, and it cannot be equal to 1 because then G is just identity. So order of G is equal to P, but then elements, then G just consists of elements identity G squared up to GP minus 1, and so basically just one cycle in this picture. And of course it means every element is a power of G. So if a group is of prime order, it's cyclic, so group of order 2 is cyclic, 3 is cyclic, 5 is cyclic, 7 is cyclic, and so on. And with groups of order 4, 8, 6, and so on, there are different options. For instance, maybe non-example, so S3 is not cyclic. And the reason is because if you take a transposition, 1, 2 has order 2, and 1, 2, 3 has order 3, and order means exactly that if you take powers, you will not get 6 elements, but you will get, in this case, 3 different elements, in this case, 2 different elements, and that's true for all elements of S3, so it means that there is no element of order equal to the size of the group, and so this one is not cyclic. So now one can ask a question, okay, what cyclic groups exist? And how many of them are there of given order? And the answer is given by a theorem, and the theorem states that for arbitrary, so every group which is cyclic is either isomorphic to Z, or if it has an elements, it is basically the group of rotations of a regular n-gon. Theorem. So two statements. So firstly, sim plus of Pn is cyclic. Group with n elements. And also every cyclic group is isomorphic to Z or sim plus of Pn for some n. So basically for each number of elements, countable or finite, there exists exactly one cyclic group with this number of elements. So proof is actually quite straightforward. So first let's discuss what the sim plus of Pn is. So first sim plus of Pn. So let's draw a regular n-gon. That's 0, 1, 2, 3, 4, 5, 6. And I'm looking at orientation preserving symmetry, so basically either a parallel transport or a reflection. And then one can easily see that if you have any symmetry of a polygon, O has to be fixed. So for any f, if you take f here, so any f here fixes O. And one can prove it in many different ways. For instance, one can say that O is a center of masses of a polygon, if you know theory of center of masses. Or you can say that O is a point from which vectors going to vertices sum up to 0, and that's the same thing as center of masses, and this was a homework problem, and then F has to preserve this property. Other solutions exist as well. So any F fixes O, so F is a rotation, rotation with a center O by some angle alpha. And then it's easy to see that since vertices go to vertices, so I can take one and see where it can go. It must go to one of the vertices. So this alpha has to be equal to 2 pi k over n for k from 0 to n minus 1. So depending on where it sends point 1, one can just count. So since every angle here is 2 pi over n, depending on if one goes to k, so if f of vertex 1, a1 equals to ak. So then the angle is 2 pi k over n. So basically this group consists of elements identity, rotation by angle 2 pi over n, rotation by angle 2 pi times 2 over n, rotations by angle 3 times 2 pi over n, and so on, up to rotation n minus 1, 2 pi over n, and that's it. So every orientation preserving symmetry of a polygon is one of those. And if I denote this angle by rotation by g, this will be g squared up to gn minus 1, and that's of course a cyclic group. So that's cyclic. So that proves part 1. So that shows 1. How to show that every cyclic group is isomorphic to one of those? So to show 2, so for 2, consider a generator G of G. So that means an element whose powers give all elements of G. So if there does not exist K such that G power K equals to the identity, then all elements identity, G squared, blah, 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 G inverse, G minus 2, and so on are distinct. Because it's just two of them coincide, just G power something equals G power something else, one divides and gets a G in some power is identity. So are distinct, and then we can construct a map from Z to G, which just sends 1 to G and n to G power n, and that's a surjective map, and also injective because all powers are distinct, and certainly sends, because of the properties of powers, sends sum to product. So that's obvious. And so if there exists K not equal to 0 such that G power K is identity, take minimal such K. That's a minimal such K bigger than 0, and every subset of positive integers has a minimal element. That's kind of induction principle. So we can take minimal such K, and then G consists of elements identity, G squared up to G K minus 1, and then when we take G power K, we get identity back. And G inverse, for instance, is G K minus 1. So these are just all elements of the group. And then we can also construct an isomorphism. So to construct an isomorphism to sim plus of Pn, or maybe it's easier to do it in the other direction, I just want to send a rotation by an angle 2 pi k over n to G power k. And quite obviously, so rotation by 2 pi over n will go to G, and then it's really easy to see that the way how I add up angles is the same as how I multiply elements of G here. So that's a proof of the theorem. So basically, there exists exactly one cyclic group for every number, infinity being countable cardinal and all finite positive integers. Okay, so in the last part of this lecture, I want to quickly discuss a usual way of thinking about this group, because usually people think of it as remainders modulo n, and that's of course a very convenient way. Okay, so this is another view of the cyclic group, and this is like remainders mod n picture, which probably a lot of you know. So consider z again, and consider an integer. So let's denote by z over nz. This is a notation for a set of n elements, which I denote by 0, 1, and minus 1. Just these numbers in brackets. And then I want to define a way to add these elements and make it into a group. So define a plus b equal to c if a plus b minus c is divisible by n. So such c exists and is unique. So such C exists and is unique, and the reason is because there is a fundamental theorem, which is called theorem about division with remainder. And the theorem says that for every element in integer numbers, there exists a, so let me maybe formulate it, is unique. So the proof is based on the following. So proof is as follows. So division with remainder, that's a theorem, and it says the following. So for any two numbers m and n in Z, where n is not equal to 0, and I took it positive integer, so that's fine, there exist unique numbers q and r such that m equal n q plus r, and r is less than absolute value of n, greater or equals than 0. So in my case, r are integers. And the picture is that you can just draw all integers, and this is 0, and this is n, this is 2n, this is minus n, and so on, and just find m here, and eventually this m lies between a certain multiple of n, which I denoted qn, and q plus 1n, and this distance is exactly what I denoted by r. And so that's a fundamental theorem from arithmetic, and if one applies it, one takes a plus b, and then there exists exactly, and then r is this remainder when you divide a plus b by n. So a plus b equals n times q plus c, where c satisfies this condition from 0 to n minus 1, and this gives the class. And basically, intuition is as follows. So you just take, for instance, n equal to 6, and then you have these classes 0, 1, 2, 3, 4, 5. And then addition works as follows. You, for instance, if you want to add 4 and 5, you just add them, and people usually just write it in these brackets. But then look at the remainder modulo 6, so subtract or add 6 a couple of times to get something from 0 to 5, and that's 3. Or, for instance, 5 plus 5 is the same as 10 is 1. So of course, with my definition, I cannot put bigger than 6 numbers here, but in slightly more sophisticated view, one views this not as just a symbol, but as a subset of integers, which gives this remainder mod n. So maybe that's more sophisticated view, is that this k is a subset of z of numbers with remainder k. Remainder k mod n. And this is an operation from z and z cross z and z to z and z, and in this way we get a group. So this makes z over nz into a group, and this group might be called remainders mod n. And of course this group is cyclic because the class of k, one can easily see, is 1 plus 1 plus 1 k times. So that's a very simple fact. And so z over nz, now we can say that z over nz is isomorphic to the group of orientation preserving symmetries of a regular polygon. So that's how one can scientifically rephrase all of that. Okay, in the last couple of minutes, I want to speak very quickly about multiplication of remainders and derive some interesting corollaries in the theory of divisibility. So now consider again the same set of n elements which are remainders mod n, but consider another operation which is multiplication, defined by a times b equal to c for c such that ab minus c is divisible by n. And again, such c exists. So unfortunately, one can ask whether this makes it into a group, and the answer is no. And the reason is because, simply because, for instance, 0 doesn't have any inverse, because you multiply anything by 0, you get 0. And it's tempting to forget about 0 and look at the rest. But that's still not a group. So because, for instance, if you take n equal to 6, then you can take a class of 2, multiply by a class of 3, and you will get a class of 6, which is class of 0. And you cannot just simply forget about 0 and get a group here. So that's what's called a ring. So that's a ring. And ring is a set with 2 operations, addition and multiplication, satisfying certain properties like in integers. Commutativity of both operations, associativity, distributivity, and such. But here is something interesting. So suppose n equal to p is prime. And let's consider z over pz cross will be a set consisting of all classes except 0. 1, 2, up to p minus 1. And operation will be multiplication with this operation multiplication defined before is a group. And a priori, it's even not obvious that this operation is well defined, because what happens when you multiply a times b, so why it's not equal to 0? But the reason is actually because p is prime. Because if we now multiply a and b, a times b equal to 0 would imply that ab is divisible by p, but then a is divisible by p and b is divisible, or b is divisible by p, because if a product of two numbers is divisible by a prime number, one of them is. But these things are 1, 2, and so on, p minus 1, so that's a contradiction because we didn't allow it to be 0. So this is why it's at least a set with an operation. So we have a finite set with a separation. Now let's see that that it is a group. So associativity is an exercise. That's a simple property of this remainders module or something, and then this 1 times a is obviously a. So this is unit. And then we need to show that the group is actually it has inverses. And why it has inverses? Because if one takes, so this is in general. So why it's a group? Because it has this property that so maybe that's a fact. So if S is a finite set such that so if S is a finite set with this what's called cancellation property, with an operation S cross S to S, such that we know that for every elements S, S1 equal S, S2 implies that S1 equals S2, then S is a group. So that was an exercise, one of the homework exercises. And the reason is because you take element S, you take all elements in your set, you multiply them by S, and because of this property, you know that you get all distinct elements, and so one of them has to be identity, so you find the inverse. And so this means that this is a group. Because it's a finite set, you have an operation, and this cancellation property is proven in the same way as the fact that it has no zero, because one can easily check that it follows from here. And so, so this is a very important group. And for instance, if you take p equal to 5, for instance, it has 4 elements, 1, 2, 3, 4, and it's an identity. Let me call it G. So this is G squared. 2 squared is 4. This is G squared. And if you take G cube, it will be 2 times 4. It's 8. It's 3. So this is G cube. So for instance, Z over 5 Z cross is isomorphic to Z over 4Z. It's a cyclic group with 4 elements. And in general, it's a theorem, though very non-trivial, or rather non-trivial. So theorem is that Z over PZ cross is cyclic. That's not simple at all. And another important corollary is that what's called little Fermat's theorem is that any number p divides a power p minus 1 for when p does not divide a. So that's a statement that in this group, if you take p minus 1 power of any element, it gives a remainder 1 when divisible by p, and that just follows from Lagrange theorem. So that's something which is a very important, maybe part of background, and I don't have more time to talk about it, but maybe we'll discuss it a little bit more during office hours.